I'm starting the stream. Hi everyone. This is going to be another Chill Maths live stream. I'm James, and this is Twitch. I haven't done this for a while. I'm sorry, I've been away for about a month. I was updating the YouTube VODs and found that I haven't done one of these since the start of December. So new year, new me. Yeah, it's more streaming. There we go. Hi to, I think Maths222 and Herb are in chat waiting for the 2 o'clock start. I think I've started, but we'll find out. My plan for this is that I'm going to do some number theory, because that's what we like around here. In what I hope is a kind of chill and relaxed way, because that's what we try to aim for. I've got a glass of water and might make a cup of tea in a minute. We're going to do a bit of that. Mary's here too. Hello, Mary. How's it going? You all right? Happy New Year. I think it was everyone else as well. New Year number theory. There you go. Yeah. I can't remember if we've had this on stream before. It's possible. This is a book called Topology of Numbers, which somebody recommended to me on a summer school in 2023. Hello, Adele, if you're watching. But it's been a year and a bit, and I've made almost no progress with it. Oh, it's tea time already. Thanks, Les Joma. And hello, Happy New Year. Hi to Herb as well. Right. Les Joma, I'm going to... Am I supposed to pause the stream immediately to make tea? Seems like not the best way to start the new year. Welcome back. Been live for 2 minutes. I'm going to hold the cup of tea just for a minute while we get at least something on screen. For people who are just joining for the first time, we have a kind of user reward thing where you can force me to go and make a cup of tea, which, then pauses the stream for a couple of minutes while my kettle boils. So it's sort of like requesting an ad break, which is a bit weird, really, when you think about it like that. Yeah, chill maths. Chill maths. Right, okay. It is chill. Good. Everyone's colours in chat have changed for me. Oh no, we had this. You worked out how you could change your own colours. They're not the same up there as they are on Twitch or in my OBS stream chat. You have different colours in all three for all of those, which just makes it harder, really. A little game. It's like if I look in different places, it's all different colours. Well, those ones are pretty close to those ones. And then those ones are all different. So I don't know what that's doing. But there we are. Okay, here's the bad news about Topology of Numbers. It's a kind of live document. That's not bad news, really. Alan Hatcher, who's the author, has done two kind of cool things. One is to put the whole thing online for free, there's a link in chat, which I think is cool. Like you can play along on a version of this at home, to download the full PDF from the author or to follow along. I think they have a webpage somewhere where you can read along. I'm pretty sure there was a web version. Maybe not for this book, but okay. You can just grab the whole PDF online, and they're updating it. Let me find this bit in the preface in here. Yes, there it is. So note on the September 24 version in the middle there. Let's make that a bit larger. If I fit that to width. Note on the 24 version. Minor revisions in chapters 1 through 7, which is most of them, a few small additions, adding to about 10 pages to the length of the book, so disaster. This was recommended to me in 23, and since then I've dawdled, and Hatcher's written more of it. So Hatcher's winning. We've got to try and keep up. So I think the cool things that Hatcher's doing, which is working on it, modifying it, and adding new stuff separately. Putting it all on the web for free. It's also available as a paper book, which you can get from the AMS on that website. There you go. I think I've due diligence. Herb's lost everything except the colour blue. Happy New Year. Here we are again. Right, okay. The weird thing I want to do is skip chapter 0, because I think the last time I looked at this, I skipped chapter 0. No, last time when we did this, if it was even on this stream, last time we did this, we looked at chapter 0 quite slowly. And chapter 0 is cool. I think I now understand what's in chapter 0. And I think I should be brave and try and look at chapter 1. Let's have a look at chapter 0 anyway. It starts at 0, which is a very nice place to start. So we're going to skim through chapter 0. If you think any of this looks cool, then you should, I guess, grab the book and have a look at the copy of the book. on Hatcher's webpage. Hello, Thrice Shy. How are you doing? Happy New Year. I like being able to say Happy New Year. It's good. It's like saying happy birthday to people, but you can say it to everyone. So that's good. I'm going to keep doing it for at least a week, I think, until I start getting strange looks for saying Happy New Year. Which one? I guess the year will be truly happy at that point. Right. So the book starts with chapter 0, talking about Pythagorean triples and talking about a very particular way to find all of them, which I think is a kind of inspiration for the themes of what's coming on later in the book. Foreshadowing, right? At the start. If not, why is it here, right? So the idea is to take your Pythagorean triple and to convert the search for Pythagorean triples, solutions to a squared plus b squared equals c squared, to convert that into a different quest to find rational points on the unit circle. So x squared plus y squared equals 1. The relationship is something like if you divide by c squared, you get these fractions that are on the unit circle, a point with rational coordinates that are is on the unit circle. Okay. And you can try and look for those instead. And then if you find one, maybe you could multiply it by the denominator or something. There's a slight wrinkle at that point, I think, but they're pretty much the same. Obviously, if you have these fractions, find the common denominator and multiply it, and you'll get some sort of solution to a squared plus b squared equals c squared. Good. Right. So that's this bit, isn't it? Find a common denominator. I'm just reading out the screen. Okay, here we go. So the calculation works like this. To find the rational points, it sort of works like this. How are they parametrizing these? So rational points, by the way, are really pretty interesting because they're kind of all the way around there. It's not every point on the unit circle because, well, there are irrational points like the one where x equals y is something to do with root 2, and you can find other examples, right, where you have these irrational points. In fact, if you pick your favourite value of theta and you work out cos theta and sine theta for a point on the unit circle, if you know about trigonometry, you know that these functions give you a point somewhere on the unit circle because cos squared plus sine squared is 1. So if you pick your favourite value of theta and find this point, it's probably not rational because these things are probably not rational numbers. Not both of them anyway. So other famous examples are sort of, you could have 1/2 root 3/2, but oh dear, one of those is irrational. If you think about that too much, it starts to feel like there aren't very many rational points at all. There are the points where the circle meets the axes, of course, but then finding other ones is equivalent to finding Pythagorean triples. So if you know about the 3, 4, 5 triangle, you can write down, divided by the hypotenuse, you can write down this set of points, which are on the unit circle, and the squares add up to 1 because the Pythagorean triple was the example earlier. Here's the way to find all other points that have rational coordinates and lie on the unit circle. You choose 1 up here, and you draw this straight line to some point over here, R0. What does R do? Is R going to be some sort of rational number? I can't remember. Anyway, well, you join a point joining up to R over here. And there's some coordinate geometry to work out. Well, if I tell you 0, 1 and R0 are points on the line, can you find this other point where it intersects the circle? And if you do that maths and sort of substitute things through, follow through and work out the point of intersection, then you get a rational answer if and only if R was rational, I think. I've skimmed through all of the details without reading them. Yeah, if R is a rational number, then this formula, so I'm skipping the maths of doing the circle geometry, check the book, or try and do it yourself if you're interested in circle geometry. So what's this last bit down here? Hello, Rice Cooker Man, how are you doing? Happy New Year. It's January and we're doing number theory. If R is a rational number, then this formula shows that both x and y are rational. This is pretty good. So if R is P over Q, then if R is a whole number, then this is definitely a fraction. But also if R is P over Q, because then you could multiply top and bottom by Q squared to get a fraction. Yes. So if R is rational, then you get a rational point on the circle. And that's already quite exciting, I think, because it means that quest of finding rational points on the circle, well, you just choose your favourite rational point over here, R for rational, and then draw this line, do some A-level maths to work out where this point is, and you find a rational point on the unit circle, which then gives you some Pythagorean triple. That's pretty cool. I think it works the other way around. Is this? There's a conversely here. Conversely means in the other direction. Something like we've just talked about, for each rational point on the x-axis, you get a rational point on the unit circle, and conversely would be the other way around. So for each rational point on the circle, you get a rational point on the x-axis. And that sort of thing's important because you want to do, for each of these, there's one of those, for each of those, there's one of these. You want to kind of not miss any of the rational points on the circle, which I think Hatcher tells me we just have. If both coordinates are rational, then the slope must be rational, that's it. Because it goes through 0, 1 at the top of the circle. The slope must be rational, and then R is something to do with the slope. It gives you a rational point over there. Right, so because 0, 1 is an example, because it's an example of a rational point, I didn't know which word to stress there, because it's an example of a rational point, other rational points have the kind of a nice relationship that the gradient between those lines would be rational, and then turns out 0, R would also be rational. It's not obvious. You've got to think about the line a bit. You've got to do some C1 coordinate geometry to work out where it is. Oh, C1 was a thing 15 years ago or something. C1 was a sort of first unit of the maths A-level, which is where you learn about intersecting lines and circles with each other. Good times. I'm not sure if it's still called that, and not everyone here is doing A-levels. Yeah, some sort of bijection, which I think it is. I think it's a bijection between... I've got to be a little bit careful. It's a bijection between points on the x-axis with a rational coordinate are in bijection with points on the circle with rational coordinates. And then there's a slight wrinkle. This doesn't quite give you a bijection to Pythagorean triples, or am I being too cautious? Maybe it does. That's coming up down here. There's a real skill to... I could just read out what's on the screen, right? But I'm trying to remember what's on the screen, which involves a little bit of me trying to remember what it says there, even though it says it there. It's coming up. I think I spend a lot of these Chill Maths live streams saying something pretty vague and weird, and then looking 2 lines down and thinking, oh yeah, there it is. There it is. I should just read on. But if I'm just reading, then I'm not joining in, am I? And joining in is how you actually get better at maths. Right. Yeah, they do. They do. On the underside of the circle. Should we do a Desmos? Let's not do a Desmos. But the ones in here give you rational points all the way down here on the circle. Yeah. Or yeah, how do you feel about negative numbers in your Pythagorean triples? How do you feel about -3 squared plus 4 squared is 5 squared? Maybe. Yeah. So what's this thing Rice Cooker Man's telling me about? It's squaring a plus ib. There are other ways of doing this, right? I have seen this sort of thing. How does the maths work? You have something like a plus ib, and that's a clever first step. Because the relationship to Pythagorean triples is something like the length of this, or the modulus of this complex number squared, is a squared plus b squared, which is a thing in Pythagorean triples. So if you knew the length of it was... What do you do? What do you do? You square a plus ib. Hello, Siri. No. Hackney. I should put spaces in that somewhere. I don't know who Prof. Borchards is, so now I'm going to quickly Google them. Thank you. Richard Ewan Borchards is a British mathematician working in quantum field theory and uses the word birational in videos. Should we look up birational as well? Maybe it means both rational. Oh, I'm Googling the word birational. It's this. I'm on the Wikipedia page. It's got this in it. Oh, it's the thing we're doing. Okay, one for later. Yes, the Pythagorean triple 0, 1, I. Have we had this before? Because 1 squared plus I squared is 0 squared. So does that mean it's a Pythagorean triple? Let's try and stick to the reals. Integers, I suppose, for Pythagorean triples. Right, what was I doing? I think I highlighted the word conversely and then foolishly scrolled down. Oh yeah, no, we talked about this. So you get rationals. Rational point on the circle, rational point on the line, rational point on the line, rational point on the circle. And you get infinitely many because you've got all these choices now. It felt like there would be about 4 or 8 maybe, but there are loads. And this is a nice thing about projection, which I suppose is that image I really quickly showed you. And this thing that we're doing, so sort of project things. We would say projection, which is supposed to be a helpful name, I think, that maybe doesn't really work that much because anymore, I don't know. These days you see a projector and you don't really know how it works, or I mean, like, I don't, right? It's a thing maybe sitting on the ceiling in a classroom or something, and it just has some internal electrics and an eye hole, and your pictures come out, right? Maybe it's got a screen that's, I don't know, see-through in a bright light or something. Genuinely magic. But I think before it was projection was maybe a more approachable technique. If you've seen sort of more stuff with old school projectors where you quite visibly have a light source that's quite distant from the thing that you're projecting to the surface you're projecting on, if you've seen something like that, or even like some sort of shadow play thing with like a bright light, some objects, and then a screen that it's being projected onto. It's a shame that these days digital projectors, I have just no idea how they work. They're sort of essentially magic. So the word projector maybe doesn't help anymore in the way that it used to. You're supposed to imagine, I think, maybe, you're supposed to imagine that these are sort of light rays coming out from a light source over here. And, well, depending on which way you're thinking about things happening, you might think about a kind of shadow puppet here, an image on the surface of this sphere being projected out. So cast a shadow over here somewhere from this light source for a sort of mapping between objects on the surface of this circle, objects on this circle, versus their shadows out here on the ground. That story doesn't quite work for the inside, of course, where the shadow is on the wrong side of the thing that's casting the shadow. But that's the kind of idea that we're supposed to have, this kind of idea that straight lines are important, and you follow the straight line from the light source to one of the objects and then to the other, where in the math sense of projection we're quite vague about which way round the shadow caster and the shadow are, because those things kind of match up. Yeah, this is stereographic projection. That's something that people say. I don't know what the word stereographic means. Maybe I can work it out. Yeah, let's not go into etymology too much, but hey, can I go into etymology? That'll be fun. Oh no. Look, whatever, okay. I've realised I don't know what stereography means. What's this different? What sort of projection is this? Etymology question for people who care about the origins of words to look up. Anyway, good. I feel like that might be one of the ideas in this book. Maybe not, who knows? This kind of projection to say finding rational points on the circle sounds hard, but you transform that problem to finding rational points on the line, and finding rational points on the line is really easy, or of the form P over Q. So it's just, yeah. I should just type etymology after my search, shouldn't I? I know. But then I got distracted and I thought, this isn't exactly engaging content, is it? Let's learn words by... can I opt out of AI overview in Google? Oh, right, okay. The word stereoscopy derives from Greek. Stereos, meaning firm or solid, and skopen, meaning to look or to see. Oh, that's an O, not an U. Come on, skop. Oh, it's here as well. Right, good. Learning Greek with James. Step 1, alphabet. Uh-oh. So looking at something firm, looking, but solid looking. Stereo, solid angle, stereoscopic, solid looking. Originally, stereogram referred to a pair of stereo images which could be reviewed using a stereoscope, which is that one where you have separate images for your eyes. Looking at solids in 3D things? Yeah, okay, I'll take that. Thanks, Herb. Yeah, that sounds good. Right, anyway, okay, chapter 0, which I said we were skipping, so here we're still going. Comments on points being dense and everywhere you look, there are loads of them. Fine, that sounds like the rationals to me because this bijection is really good. And then finding the Pythagorean triples, what do? So you multiply up by the common factor to get formulas like this. Yeah, so it's all Pythagorean triples. This is the wrinkle that I vaguely remembered. Up to multiplication by constant, because you're going to create things like... You might accidentally make things where there's a shared factor. Yeah, if I take P and Q to be anything, then I might make things with shared factors. Yeah. It may not be primitive. Yeah, both even. If P and Q are both odd, then you get things where both even, so it's even. So maybe finding the primitive ones is hard. Yep, maths 2. I think there's a fact a bit like that the circle S1 is so S1 is like the reals with a point at infinity. What's that called? There's a word for that. That's called completion or something. So you take the real line and you bend it around in this way using projection to say, aha, I'm going to take the real line. I'm going to find all the points on the circle which cast shadows at each of these points on the ground. And what you find is that points very far away now come into view, because if you put your shadow puppet right near the North Pole where the light is, its shadow would be very far away. So if I'm going to wrap up the reals, that very far away point comes into view because it ends up being very near the North Pole. And then the idea for maths 2 in chat is to just put that point in as well and label it infinity. There it is. This is sort of a natural place for it to live. Is right in this gap. And then you get this model of the real numbers together with this extra point at the North Pole. You bend around the real numbers with all of the very distant points getting closer and closer together as they get closer to the North Pole. You add in that point at the North Pole. That gives you a model of the real numbers. Because you've done a thing there. This isn't quite... It's tempting to think, so it's tempting to see that model and to think this reveals a fact about infinity, right? Because one thing you could now say is, looking at my circle, if I go round the circle, maybe I should have a circle on the screen. Oh, you know what circles are. If I go there, so it's this little gap at the top, which we're going to label infinity, and I'm going to put a sort of question mark next to it. Because one thing you might think when you've seen that model is, aha, I now understand infinity, right? You go out to infinity, and you keep going round the circle, and as you keep going around the circle, you get back into kind of negative infinity at the same point, and you come back in again. And you'll keep going round. And it's tempting to think that this gives you kind of an understanding of infinity in the reals. But, of course, infinity is not in the reals. And the thing that you've done here by gluing them together with a single point is a sort of construction that you've done. And you have to remember that a little bit. If you're trying to use this to understand the reals, you have to remember a bit that you've added in a kind of extra thing. So it's very tempting to think, aha, so this shows you that minus infinity must be the same thing, but you could put 2 points. Yeah, right. It makes you think about 1 over x, right? I feel like I've had this discussion with people before, possibly people in chat. But the thing that it's very tempting to talk about now is to say, well, if I've got the graph of 1 over x, that has this behaviour where it goes off towards minus infinity over here, and then sort of comes back again from infinity. So in our circle model of the reals, it's a bit like it's gone around. I can do it with the red spot. It's gone around here to negative infinity, and then suddenly popped back at positive infinity, and that's quite nice, isn't it? So it's sort of going around. It kind of feels like this maybe gives you some understanding of what's going on there. But then you kind of separately have to understand the function 1 over x squared, which doesn't do that at all. It goes to infinity and then it comes back down again from infinity. So there's something subtle going on. You can't just say, aha, when you go to infinity, your sequence will then briefly be undefined and then come back from the other side, because that's not even true. So there's sort of some other things. You've got to be careful with these models. There's a cautionary note on saying too much about the behaviour of real functions based on adding in the infinity. Right, so then this book is going to talk about Pythagorean triples, and that's going to be fine. We're going to be okay. Yeah, okay, so we're multiplying up. What is this? Is this going to go through? So this now gets very Pythagorean triple-y, doesn't it? We'll just talk about the primitive ones. Perhaps obtain from this by letting P and Q range over all positive integers, P greater than Q, such that P and Q have no common factor and are opposite parity. So this is ruling out all of the... It's carefully restricting what numbers I'm allowed to take for P and Q. I spotted that you could have common factors, and the text above talked about having the same parity, so that it would be all even triple. And apparently that's enough. They now don't repeat. So they're primitive. So this is going to be checking that under these conditions, you have, you've got to check if they're primitive. Okay, good, right. But this seems like a specific Pythagorean thing, right? Hopefully, maybe. Anyway, do some number theory. Good. I think I have read through this before and found it quite hard going somehow. It's hard to stay there. Hello, Mean Machine Rex. Good to see you in chat. Happy New Year, as I'm enjoying telling people. You've got a little thing that says 2024. What does that mean? Oh, you did Twitch Recap 2024. Ooh. Cool. Okay. We are skim reading through chapter 0 of a book. I can't remember if I've talked about it on stream before. Happy New Year. It's this book in chat. And I'm trying my best to skip over details, because for this particular book you can get all of the details yourself online, because the author Alan Hatch has made the whole thing available. Okay, right, so there's this bit about quadratic forms to talk about. I don't remember this bit. Ask a question for Pythagorean triples. The remaining ones are obtained by multiplying by arbitrary positive integers. Okay, here's our formula. No common factor, opposite parity, and P is greater than Q or something. Not both odd. It cannot be fine, whatever. Oh, so P greater than Q is so that you get a positive number in the middle, I think. Anyway. What am I doing? Yes, okay, so it's turning into a quadratic forms question. We've seen quadratic forms a couple of times on this stream, because a few times I've looked at like sort of number theory notes to find out what comes next after you've learnt about modular arithmetic, right? What do you do next? And the answer really seems to be quadratic forms. It seems to be quadratic residues, maybe, are the kind of main things that people seem to talk about in a second course on number theory. And I've never really got to grips with them. Maybe that's 2025. Okay, so they look like this. It's a number on the right hand side. The question is to work out whether they have solutions or not. It feels like questions we've seen in other places, like finding at one point, maybe last year, we were interested in integer solutions to a kind of Diophantine equation that was quadratic, I think, and they were going to give us rational approximations to nice numbers. There was a point where we were working out whether numbers could be written in the form n squared plus 1 or something like that. Not that form, sorry, written in the form. Numbers of the form n squared plus 1 could be written in the form n squared plus 1. But what were we doing? Were we trying to write things as the sum of two squares or something like that? Right, so it's the sum of two squares is a quadratic form. So the question, which numbers can be written as p squared plus q squared for integers p and q, is a question of quadratic forms. Circle seems relevant for that one. As does Yeah, okay. So what's this? Let's move that out of the way. I don't remember reading this before, so maybe I'll go through it a bit slower. And then, 2:30. I've got to have a cup of tea at some point quite soon, haven't I? Because it's been half an hour without a cup of tea. Oh. Difference between two consecutive squares. That sounds true, because yes, there's consecutive ones. Good. That's how that works. Primitive triple. We've shown that all positive numbers. So, what are we trying to achieve here? We're sort of talking about whether numbers appear in primitive Pythagorean triples or not. And some of them do, because they can be the difference of two squares. These ones do, but none of those ones. Okay. Can be realised as a non-primitive triple because it's twice 2k plus 1. Oh, so this is the different sorts of evens and which numbers. All numbers can be realised. That's a fairly good punchline. Okay, that's a fairly good punchline. All numbers can be realised in a Pythagorean triple. As A or B. But then this question about which numbers can be written as the sum of two squares is the one that we've seen before in other number theory books. So Pythagorean triples give us solutions for squares. What about other ones? Okay, and then if you work out when C appears in primitive triples, then you can multiply up. Earlier table seems to show that the numbers C can be realised in primitive triples. Fairly rare, only these ones occur in the table. In fact, they are all of the form 4k plus 1. That's a fact we've seen before on the stream, I think, that only of the odd numbers, only numbers of the form 4k plus 1 can be written as the sum of two squares. There's some sort of proof using complex numbers for that one as well, I think. So one is an even number and the other is an odd number. Good, they're multiple of 4 plus 1. That's a separate proof with no complex numbers. And now here's the congruent mod 4 stuff. What are we reading? Someone do what in chat for me, please? We're reading Hatcher's Topology of Numbers. We're on chapter 0. I'm trying to get further with it than I've ever got with it before, and I'm struggling to remember where I got to. Thank you, Herbert. There you go. It's number 3 for the new year. Happy New Year, Megalomorph. Right, what am I doing? Summary of modular arithmetic, great. Sum of squares. So somehow, even in chapter 0, I think this is a proof that numbers that are sum of two squares have to be 1 mod 4. It's quite good, because last time we read some number theory notes, I think that took ages, but was quite a separate thing to what we were doing. I've changed some settings so that you can see commands in the thing on Twitch stream, so that if you're watching the Twitch stream or the video on YouTube, then you can see stuff that happens in the commands. I also changed the symbol. I also changed the setting that made the font size different, and then I panicked and changed it back. And I don't actually know if I've set it back correctly or not. It was tiny for a bit. I'm always trying to battle that thing about trying to get people's text to line up with the box that's up the screen. It looks like an object. It's actually about 4 objects stacked on top of each other and not quite lined up with each other. Twitch. Oh yeah, Herb worked out that you put an exclamation mark at the start and it doesn't get recorded in the VOD. I remember that. That was fun. I don't know what happens if you... Anyway, never mind. We can probably find... Other Twitch features are available. Right, what are we doing? Maybe we're making a cup of tea. Most of these are primes. Oh yeah, there's this fact about... Yeah, okay. Yeah, products of primes congruent to 1 mod 4. But coming at it from a different angle, right? First prime satisfying position is not on the original list of 73, and that actually comes up later. As, oh my goodness, look at that triple. Wow. So what's this p squared plus q squared? What are we doing here? 64 plus 9. So you write 73 as the sum of two squares. What's that got to do with the I've got lost, you see. I haven't been paying attention to the maths enough to know what's going on. Oh, so p squared plus q squared was the denominator in... so the formula for Pythagorean triples has p squared plus q squared. So p squared plus q squared as c? Yeah. So how does that help you? Oh no, okay, so we know we're talking about the number c, which then gets squared to actually be in the Pythagorean triple, right? So it's kind of weird, like the hypotenuse is, I find this confusing, p squared plus q squared, which looks already very square because of the squares. But of course in Pythagoras' theorem it's going to be squared, that's the hypotenuse c, it's rolled to be squared again. It's sort of c squared in Pythagorean. That's not clever. That's not a clever thing to say and have recorded on Twitch, but you know, look at all these squares. Theorem's supposed to be about triangles. What are all these squares doing? Right, okay, so the conjecture in chapter 0 is that the numbers you can write as the sum of two squares are the product of primes that are 1 mod 4. As a prime, not doing this. And these work out. And I have seen a thing about products. So really the question is, which primes can you write as the sum of two squares? Because there is a fantastic result about what happens if you know that a squared plus b squared equals n and c squared plus d squared equals m. There's a fantastic way to write the product nm as the sum of two squares. It's really good. It's something like this. AC minus BD squared plus... Oh, I'm going to get this wrong. It'd be really annoying to get this wrong. I think I'm going to get this correct and then have a cup of tea to celebrate. If and then. I think that's right. The joke here is that it's all complex numbers, really. We had something about that in Twitch chat earlier, but the joke is that you imagine this as the modulus squared of a plus bi, and this is the modulus squared of c plus di, and then you pretend to think really hard, but you try to multiply those numbers together in your head, so that you get the modulus of a plus bi, c plus di. So this is, if I put squares on it, no, modulus I don't have to square anything. I don't have to square anything. This thing is an nm, is supposed to be the product of these things, but then this is the sum of two squares. So Meglemorph says, result in chat, the primes that are sum of two squares are exactly those congruents 1 mod 4, and then you can build other stuff, right? Numbers that are sum of the two squares are those where each prime q congruent to 3 mod 4, which defines how much appear to an even power. Right, because you can always multiply up by a square. So you can do products, so you can glue these things together, which lets you get as many 1 mod 4 primes as you like. But then those 3 mod 4 ones, they're also okay, because if you have some sort of prime squared, which Meglemorph says that if the prime is 3 mod 4, then we can't write that as the sum of two squares, but we can write it its square as the sum of two squares. So then you also get a p squared to play with, even for these unfortunate 3 mod 4 primes. Okay, right. But we haven't proved that yet. We've just looked at some primes that are 1 mod 4, and then I think it's going to be the aim of some of this. Is that what this is going to say? Is it conjecture? Proving it is not easy. We will do this in chapter 6. Right. Okay. So I thought we'd got it here. What did we get here? Here we know that the sum of two squares. No. What? Over there we know that it's necessary if P and Q have no factors in common, then one's even, one's odd. So you get something that's 1, 1. You get something that's 1, 1, 4. Going the other way, well, you have something that's 1, 1, 4, and actually writing it as the sum of two squares is hard, and that's happening in chapter 6. Okay, right, okay. So I thought we've done it very quickly, but in fact we'd only done the easy direction, not the hard direction. Okay, good, right. Hi Neutrino, how's it going? Happy New Year. Megamorphs are proof. Yesterday, they used Wilson's theorem. I feel like I've seen it at some point as well. Wilson's theorem is very cool. Yeah, something like, how did that work? The square root. So if your aim is to write a prime, so the sum of two squares, how did this work? Feels like a Kettle question. Oh, do I need to turn down the number of points for T? It's already, I'm one behind. I have one waiting for me in Twitch from last January, from like 40 minutes ago. Okay. Right, so this is going to be a question for later on, or we remember Wilson's theorem enough. I feel like it was the Wilson's theorem approach. What did I do on Unique last year? On a summer school last year, I did Wilson's theorem and then tried to do something mad afterwards. Yeah, it was to show that -1 is a square root mod p. Oh, mod p. -1 is a square mod p. But mod p is not enough, is it? Because then that would be that a squared plus 1 is a multiple of p. But that's not what we want. We want p to actually be written as the sum of two squares, not 1 more than a squared. That's what I've done with Wilson's theorem before. Was that even using Wilson's theorem, or just a slightly related to Wilson's theorem? Good times, number theory. Right, okay. I'm going to have a quick look at how much of the preview we've got left, and there's more than I thought. Good. What is this question then? How many of them are 2, 3 different by 1? That's a simpler equation, right? The pair of numbers that are different by 1 get larger. Approximately. Oh yes, these give me us approximations of root 2. Hopefully, good. Here are some, and they give us approximations of root 2, which is very nice. We will develop. Could there be other solutions of this equation with smaller numbers that we missed? Yeah, good. Okay, so we will generate some. We will generate some approximations to root 2 if we read chapters 4 and 5, because with these very large numbers where the sides are approximately the same length. Oh no. Okay, what's this? Where's the 45-degree triangle gone? With these ones, right? If A and B are about the same. Oh, where A and B differ by 1. Where A and B differ by 1, we get some nice approximations for root 2. Like, so this one's a triangle where the sides are almost the same, so it must be about the 45-degree triangle. I've lost the number 45 on screen. It was on screen a second ago, wasn't it? Maybe not. Oh yeah, here they are. Good. What is this then? Pell's equation, yeah, good fun. You find, I got these. Oh my goodness. The smallest positive integer solution to this equation is these huge numbers. I've seen these before in various maths camp kind of things. Here's a section on complex numbers for fans of complex numbers. And I'm going to skip it, I think. And some Gaussian integers for people who wanted Gaussian integers. Again, if you want to play along at home, Hatch put the whole book online. So if you want to read a bit about Gaussian integers, there's a bit in chapter 8 as well. Right, what are we doing? So there's some generalization to talk about finding these on quadratic curves instead. So other circles, no obvious rational points, so we don't know where to start. And then maybe that's proof and some foreshadowing about all of those. Oh my goodness, there's way more of a preview than I thought. I don't know why I thought it was going to be a quick job. Happy New Year, Stucky. How's it going? Oh, Fermat's last theorem, great. Having a wonderful time. Also, be aware of cubic caps. Right, my goodness, why is this still going? I really thought I'd read the preview before. Turns out maybe I haven't read the preview before because I'm surprised by how much stuff is in there. Oh, and 3D, higher dimensions, great times. Find triples, x squared plus y squared plus z squared. Oh yeah, equals 1. Yeah, that seems like a sensible diagram to draw, doesn't it? What is going on here? Hi, Stucky. I'm rushing through the preview of a book because I want to get on to chapter 1, where I suspect the kind of content starts again, rather than looking at a preview of absolutely everything. But there is way more preview than I thought because the book is way larger than I thought. Hey, there's the word stereographic projection. Looking at 3D things with both of your eyes or something. No, that wasn't what I meant. Stereo meant solid, not stereo like speakers. Good, right. That's a cute thing to say. This geometric viewpoint somehow makes infinity less of a mystery, as it just corresponds to a point on the sphere. And points on the sphere are not very mysterious. Though in the early days of polar exploration, the North Pole may have seemed very mysterious and infinitely distant. That's good. I like that. Right, what are we doing? None of this. We're skipping through all of this now. Other questions about Diophantine equations aside, we fit the exercises. Right, okay, that was a skim through look at chapter 0, because what I really wanted to think about today was fairy diagrams. And arguably, we should probably have understood chapter 0, really dug into the mechanics of what's coming up later on in chapters 4, 5, 6, 7, and 8. But my hope is that chapter 1 on its own has enough kind of stuff going on. This is a very good diagram. The preview has exercises, yes, it's a book with a lot of stuff. And 3D, right? It's everything we could want, right? It did an extension to 3D, it did an extension to complex numbers, high dimensions, it did bits and pieces on a variety of things. We're going to take a quick break because I'm going to make a cup of tea. You're welcome to make a cup of tea as well. If you would prefer to use your break to look at some of that stuff that we just skipped over or try some of the exercises, then once again, this book that we're looking at is just freely available online because Alan Hatcher is cool. After the cup of tea, we're going to talk about this picture, which is on the cover of the book and has points on the circle intriguingly labelled with rational numbers, including the rational number 1 over 0, which I know I tell you not to do, but there we are. So there's going to be an ad break for a couple of minutes here. If the screen shows you an advert, then you're welcome to think about maths instead. If you feel like buying any of the things in the ads, then I think that indirectly helps Twitch or something. I don't really understand. But there you go. Herb's left a box of tea somewhere in the... No! Okay, Herb needs to be shown ads for tea or something. Acquire additional tea. That is disaster of the day. Whoops, my goodness. That's gone to sleep. I'm going to take a break as well. Back in 2 minutes. It's back. Whew. Right, okay. I can't remember how to do this. Yes, I can. Run an ad break and mute. Back in a minute and a bit. See ya. think I'm back. Ooh, Twitch now says unstable. I don't know if that's a comment on me or a comment on Twitch. Who's opted out of ads? Is that a thing you can do? What's going on? Oh, Twitch chat's just been running. That's great. I don't even need to be here. It's content. People doing things. Thanks for hanging around if you're around. Ooh, I don't know what a modular form is. I'm willing to put that in video. Why is that blinking green and grey? What's it trying to communicate? I was trying to tell me that I can't run an ad. Great. Still not used to Twitch. I'm really surprised you can just have a whole chat about modular forms. I only know about modular forms because they're in the documentary about Fermat's last theorem, which, if you haven't seen the documentary for Fermat's last theorem made by the BBC, it's really good. But it's also really 90s, so you have to be able to engage with media from before the millennium. Has some quirks that are quite 90s to it. But that was when Fermat's last theorem was proved, so that's when the documentary was made. I like that, and they have one visual to try and talk about modular forms. But yeah, Dr. Zegler talks about modular forms on YouTube. Okay, are they the ones where sort of AX plus B over CX plus D, possibly with constraint, or have I just made up some nonsense? Yeah, sort of, with some constraints. Yeah, okay. Another day. There's maps of circles. I'm thinking of Mobius maps, which is not quite the same thing at all, but I'm going to blag it, so here we go. Yeah, Mobius maps of the form AX plus B over CX plus D. They're great, and they tend to map circles to circles. And yeah, what can we see on the screen? Challenge before. The actual diagram has infinitely many curvilinear triangles. So curvilinear is probably a new word for some people watching. Might think, curve and a line at the same time. Interesting. Let's not worry about that. I think these are all circular arcs that meet the circle around the outside at right angles, which is, it makes me suspicious because at some point in university I did a whole course about these kind of Mobius transformations, these kind of conformal maps of the complex plane that preserve angles. So when I see circles meeting at right angles, what I think I'm supposed to think about is lines meeting at right angles to which someone has applied a Mobius map. The thing about Mobius maps is they send lines and circles to lines and circles. If you start with a line, you get either a line or a circle. And if you start with a circle, you get either a line or a circle. They kind of blur the boundaries between those things. So is this the image of some sort of... Oh, what is this? We're going to work out what this is in a second by reading the text, of course. That's how we do things, but it's nice before that to stop and think about what we're looking at. I'm going to briefly sneeze. What's the etiquette here? Other streamers, other people who watch other streams, what do they do when they sneeze? Am I supposed to just sneeze on stream? It feels like that's not advisable in terms of... It feels career-ending, to be honest. A sneeze on stream. There's a microphone and a camera. Worse. Am I supposed to like really quickly go to a chew and then back again? Is that what people do? Lightning reflexes on the buttons? I don't know. Oh, just sneeze and then pretend it didn't happen. Amazing, right? Well, I look forward to that. Mute if possible. Goodness me, there's people out there with headphones and stuff. Okay, is that a little glitch for anybody else? I'm going to not look too closely at the glitches. Okay, so the second thing we notice after all of the curves and circles is the numbers around the outside, right? Like a demented clock where the numbers don't go in increasing order, right? For example, here is 1. Can we find the number 2 on this clock? Ah, yes, here it is. 2 is over here, and then 3, and then 4 and 5, which gives me this horrible feeling that 6, 7, 8, 9, 10, and so on might be in here before we hit 1/0 on that side. Looking around here, it looks like these numbers on the left are all larger than 1. These ones are all smaller than 1. These ones are negative. And is there a relationship? This is negative of the thing above. Yes. There's a nice positive negative thing going on. It's nice to look for these things before reading on. What will happen is we'll turn the page and this will all be on the next page. So then I guess we'll feel slightly silly for thinking, but also we get to feel slightly smug for thinking about it. Robots don't sneeze. Right. Hey, here's 0. I should have included that in my looking for numbers. Oh, I guess so. So -1 is down here, and then -2. So there's some structure to these arcs as well. I don't know if this is obvious, but it looks like each arc kind of contains 2 small arcs. I mean, there's loads of arcs everywhere, but there's kind of this large arc making these. I sort of see these 4 ones in the middle. I suppose this straight line maybe counts as well. Straight line across the middle. If you relax your mind to think of lines and circles as all being kind of the same thing, it meets at right angles. That's fine. Then you get this kind of quarter circle, which rather pleasantly meets the outer circle at right angles. And then these smaller ones, and it looks like they meet at right angles as well. So I don't know the relevance of using circular arcs or right angles or anything. I don't know what the lines are showing me yet. But it looks like if I wanted to make this again, that's a challenge perhaps. If it goes away from the screen, could you build it again? Could you draw it yourself on a bit of paper? What were we just looking at, right? But I found out how to blank the screen by mistake. It does make a pretty picture. But maybe it also helps us see that kind of thing about midpoints going on, right? If there were an angle to this, then it'd be a bit missing. Maybe that'd be fine. I guess if you're drawing a line, it's got to meet at some angle over here. Why not 90 degrees? So this halving thing, I mean something like this is at the kind of halfway point between, well, there's this big arc, and then the halfway point has these slightly smaller arcs, and then the halfway point again, so it's 3/2 and 3/1 over here, and I can see this keeps splitting in a kind of hierarchy. Mumble mumble fractal, mumble mumble self-similarity, mumble mumble, whatever. This seems important. Okay, so the lines are maybe highlighting this kind of structure of maybe where the number's coming from. Maybe something's acting on this. Good. Oh, can I remember what PSL2Z all stands for? SL is special linear. It's the determinant 1 stuff. I cannot remember what PSL2 was. What the P stands for. Projective special linear group. Oh, and it's the thing I said. So what's SL2 then? Oh, minus signs. Fine, okay. Okay, so special linear group. Special linear group includes things with a determinant -1. Fun, matrices, woo! Okay. What's the difference between PSL2Z and SL2Z is the question of the day, I think. Maybe I'm not correct at all. Okay, right, Megalomorph can tell me in chat, because SL2Z is the thing I remembered. PSL2Z is the thing I said out loud, so maybe it's the thing I should have remembered. None of that made any sense. Right, here's how to construct it. 2 big triangles with curved sides, but whatever, and then adding 4 triangles that share an edge with 2, then 8, 16, and so on forever. Okay. With a little practice, one can draw the diagram without lifting one's pencil from the paper. Right, yes, please. First draw the outer circle, then the diameter. And you have to start from the left. Then make the 2 large triangles, then the 4 next largest triangles. Right, here we go. Welcome back to ArtStream. Circle, I'm going to do it tiny as well. Diameter, 4 small circles, 8. Already time for 8. Here we go. 8 tiny ones going to the midpoints, and so on forever. Acing this. Excellent stuff. Oh, I curved the wrong way. Oh, it's got worse on the way around. Perfect. There we go. Is it a fractal? I never really know. There's a 3 blue 1 brown video about fractals and self-similarity, which has reminded me that I don't know the definitions of either of those things precisely. Thank you, Megalomorph. That is what I needed, by the way. Yes, cheers. You made it all about Mobius maps again, which is something that I do remember. Yeah, good. Did we do whole art streams? I don't remember. We definitely tried to draw more things in the past. I'm more ambitious with the drawing before. Maybe another day. Like peeling an artichoke. Wait, but kind of backwards, right? Because if you're peeling something, you have to start on the kind of tiniest outside bits. Or maybe if you're pulling it apart, yeah, okay. Like you're pulling something apart, and you split it in half, and then you pull off the outer leaves, and then it's got little bits that you pull off as well. Yeah. Maybe she could draw. There we go. Okay. Medium rule. Here's what's going on with the numbers. Oh, right. Right, first label these, including 1 over 0 for infinity. I'm going to write it like that. In the upper half of the diagram, first label the vertices of the big triangle like this, then add labels for successively smaller triangles by the rule that if you have a plus b and c over d, then you put this number in between. And I love this, contrary to the usual way of adding fractions. I think when you first learn about fractions, maybe this is the usual way of attempting to add fractions. It doesn't give you mathematically the total, but it does give you a fraction. Add the numerators, add the denominators. It's a shame that's not how it works. That goes there on the thing in the middle, and I need to learn this word called the mediant. I think we're going to prove this in a page or two, but I think it lies in between A over B and C over D. If this one's smaller than that one, then I think this is somewhere in between. And I can't tell if that's obvious or not, because that's not how you actually add fractions. Is that obvious? No, maybe not. Well, let's try and prove it in sort of one line or something. If A over B is less than C over D, then what I would like, A over B, let's multiply it by B plus D. Well, let's multiply up and do A, B plus D is AB plus AD, which is greater than, if I multiply up on the other side, I want AB plus BC. And that AD greater than BC thing is just true. Ooh, have I got my signs the wrong way around? I've got my signs the wrong way around, but I can fix it like this. Is less than this because AB is the same in both, and AD is less than BC is the fact in up we're given by this thing. So, and then dividing. Dividing's fine because everything's positive. Okay, so let's put an if up here, and all positive. Then we're okay. So then this thing is in the right order, and I'm going to assume that the other one is true. Okay, I have that as not obvious, but well, the way I've proved it doesn't make it look obvious, but makes it look like a chore to prove. But seems like if these were in the order A of B less than C over D with all the numbers positive, and might as well be, right? Well, I guess I have to think about negative fractions as well a little bit. Which ones do I need to be positive? I'm multiplying up by BD in here, and I'm multiplying up by B plus D b over here. So if the denominators are positive, so I only need to require that the denominator is positive, and then my maths should still work for negative numbers, because I'm only multiplying up by the things to do with the denominators of these fractions. So for the negative ones, I'll write the minus sign in the numerator, not the denominator. You're allowed to, it's still a fraction, but I'll choose to write it in the numerator. I'm with Neutrino. There's some definition out there of fractals, but I don't remember what it is. I'm not certain that the definition of fractals, if there is one out there, maybe there's competing definitions as well. There's always something that can happen. Not sure it helps you. Well, how much does it help you? Depends what you're trying to do with fractals, really. Anyway. Right, what are we doing? Oh, look, down here. Down here. This happened again. I've done a little bit of math myself, and then red on, and it's in between. In the proper order around the circle. Obviously true for integer labels. Verify it, show this. That's what we want to show this. Positive denominators. It's one of those times where the maths that I did on the screen was just off. I should just have scrolled down, but no, I'm glad I did it and then scrolled down and saw it down here. Reading maths books is hard. Good, it's been proven in exactly the way that I did it, which makes me think that it's not obvious. If this had said something different and said something sort of, this is some linear combination of these two with parameter in between, but that's not what it says. So maybe that's the best way to do it. Yeah, fractals don't have to be self-similar is the title of a 3 blue 1 brown video. Let's see if we can find it. Fractals are self. Sorry for the keyboard noise. Can I just drag this? I think I can. Is called Fractals Are Not Typically Self-Similar by 3 blue 1 brown. Apparently 7 years ago, time flies. 8, now it's 2025. Happy New Year. I dragged. Is that a good job because I dragged a link correctly? Or yeah, well, never mind. Here's another version where it's been straightened out, and now you get to say stuff about Mobius maps, I think, because turning a circle into a straight line but keeping all of the circular arcs as circles, well, everything looks nice now, doesn't it? Why are there so many of these vertical? Oh, what's going on here? Oh, those are integers. Those are integers. Oh, under stereographic projection, is this just going to end up being actually the reals all in the right places? That would be nice. That can't be true. No. That can't be true at all, can it? I've noticed that 1/2 is in the middle. And 1/3 is closer. Well, let's read it. Is it just the stereographic projection of this? I'm suspicious because... No, I don't think it is. I think this one has been distorted so that the numbers are actually in the right places on the real line. Vertex 1, 0 is at infinity. Edge of the diagram shows vertical lines. Semicircles, then points. Position these. It's actually the number. We can position these. Place the new vertex at any point between its outer two vertices. We just choose this to be the median. Okay, and then you do that. I'd be amazed if this is like beautifully related to the circle model by some sort of nice transformation. That would be really cool. I don't think it is. So 4/3 is the median of these things. 5/3 is the median of those things. In the real world, on the real line, you want those things to be closer to 3/2 than they are to 1 and 2. If you just do a projection, I think the distances will be the distances between these 4 things, 5 things? The 4 distances between these 5 things, I think, be monotonic. Because they're all the distances between these, where are they? the distances between, here they are. I think it'll be monotonic if you just project down, like further away things. These ones will be close together, these will be slightly further apart, these will be far apart, and these will be quite far apart on the projection. So I think it's not quite projection that gives you the relationship between these two pictures. Something else. Hello, Phobos Stream. How's it going? I missed you. I missed you there. You all right? Happy New Year. That's what we're saying. Look at a cool diagram with lots of semicircles. I don't think I can draw this one without taking my pen off the page. So is it weird that I could draw the previous one? Yeah, okay. Wait, surely I can because they're kind of the same. Oh no, it's got all these lines that go off to infinity. Is that alright? All the numbers. Why are all of the numbers joined to infinity? Were they joined to infinity before? Yes, because each time you make a number, you find the median. Here's the fairy diagram. Packing for a trip. So much stuff. Packing on the way home is easier, right? Because you just have to pack. Well, packing while you're on the trip is then easier because you pack everything that you can see. I've thought about this a bit as a sort of problem-solving thing, but I haven't quite worked it out. Like, packing's not hard, it's the deciding what to pack that's hard. And you can tell because when you're packing to come home and just have to put everything in. Like, leaving a hotel is easier than preparing to arrive. And never mind, okay. It's sort of like isolating the problem aspect. Anyway, never mind. So here are some whole numbers over here. And there's kind of these different arcs. So these ones, lovely sort of fountain outwards of circular arcs, they go to the integers. So in this other version of the diagram, where the integers are in their normal places along the number line, we see lots of lines joining up to infinity. Yes. Okay. I'm disappointed, I think, that it's not just a stereographic version of the previous one, but yeah, it's all powers of 2 over here. Stereographic projection is more like not powers of 2. Anyway, what's going on? Oh no, stereographic projection. No, really? No. Oh, but this one's distorted, I think. In the previous chapter, we described how rational points on the unit circle correspond to rational points, yes, by means of lines. Using this correspondence, we can construct a new fairy diagram in the circle by filling in triangles and median rules before. Okay, but I think Crusoe is going to be different, right? Yeah. Perturbations to the positions. Fantastic. There we go. Well, not fantastic. I mean, it's a shame that it's not the cool thing. The cool thing would be if it was exactly the same. Yeah, but we'll just think, okay, fine. You'd have to figure out where to put stuff. Okay, so sort of, is that topology? I don't know. The actual distances don't matter. Stop thinking about distances. Start thinking about relationships. I don't know. So now we're doing Pythagorean triples again. New circular one. Oh, this does look a bit distorted, doesn't it? It's rotated. And what's it doing? And Pythagorean triples using this. The vertex with label P over Q is a rational point on the circle. Ooh, gosh, right, okay. So the rational point, so it's been labelled with some number. Labelled with some number. What's the relationship between the A's and B's and P's and Q's? Is it the Pythagorean triple stuff? Right, so there's the relationship between A's, B's, and P's and Q's. My goodness. So you take a rational point on the real line, you project it onto the circle, and previously we would say aha, so you started at, what was that, 5 over 12 or something? No. Vertex with label. So where did this come from? it come from P over Q? Possibly. The bloody time we hate distances. If a horse is going on a trip, it means distances are very important. Or maybe places are important. Anyway. Ooh. Right. Am I buying tea? What's going on in chat? Oh, I missed Cyrano Hakenji saying, can we do this in Python or graph it? I think that sounds like a good task that is probably within like, I guess say within your skill set, right? The tricky bit that we haven't talked about yet is going to be none of the drawing. The drawing's fine, I think. The tricky bit, I think, is going to be working out the geometry of these circles. The specification here to draw the thing you're trying to draw is you're trying to draw circular arcs, not semicircles. Circular arcs that meet the big circle at right angles. That's not impossible. It's just a bit of geometry to try and work out where to put those. Or if you like the transformation stuff, then you can solve the problem on the real line to work out where to put the circles. Can you transform? I'm not sure if you can transform. No, because the centers would all be on the real line, right? And that's not what's going on here. Is it? No, that's not what's going on here. The center of this first arc is over here somewhere, which is not its projection at all. How could it be? Projection only gives you points on the circle. Oh, are we having fun? Right. Right, have I understood this? We're labelling, so we've got Pythagorean triples. I think I haven't understood this, which is fair enough, right? So we took the point 4 over 3, which is a rational point on the real line, and we projected it along a straight line up to here. So 1 is here, 1 ends up here. 4/3 ends up a little bit bigger than 1, ends up over here somewhere. 2 was all the way over here. 2 4/3 or something. Straight line. Straight line, perfectly straight line. It went through all the points I care about. Let's try again. Yeah. Got it, right, okay, so 4/3 went in here. And then is that P over Q? The vertex we label P over Q, right, okay, has coordinates which we worked out because we did all that geometry stuff in chapter 0. And it corresponds to a Pythagorean triple then, if you multiply it by p squared plus q squared. So 4/3 on the real line gives you this Pythagorean triple. 24 squared plus 7 squared is 25 squared. And if you write p over q in lowest terms, for a fraction greater than 1, then you get something in primitive form, I think. I think that's what we said before. But anyway, okay. Good. Whoa, what are we doing? Ooh. If you do this construction like this, so we've done this, they're saying inductive process. We keep drawing more and more of these arcs. Not easy to tell whether or not two numbers are joined by an edge. And why would they be joined by an edge? 1/3 and 1/2. Because they're going to fit together in the hierarchy. The 1/3 was calculated because it's 0 plus 1 over 1 plus 2. That's the mediant rule. You have to know these things are connected. If at some point in the hierarchy you were planning to add them, so if one of them was the mediant of the other and some kind of mystery third point. Goodness me, that is hard to think about. But here is a simple rule to work out whether two things are connected, which is even if the determinant AD minus BC of this matrix is equal to plus or minus 1, matrix time. Not tea time, but also matrix time. Who was talking about matrices before? Wait, who was it? I've forgotten exactly who it was. It was Megalomorph was telling me about matrices earlier. Here's some matrices. Sometimes I feel like matrices were sent to punish me, but it's unduly deserved. Says more about me than it does about matrices. Right, okay. So the observation perhaps is that these things, you calculate AD minus BC and you get the number 1 or minus 1. That's true for the starting points because of their fun combinations of zeros and ones. 1 minus 0. Oh no. Yes, it's all leading to a Mobius transformation, isn't it? Here it is. Here's the thing that looks like the determinant of this. This is all leading to Mobius transformations, which is great. It feels like it's moving more towards my home turf. Yes, that's right. I like Mobius transformations, but don't like matrices. Fight me. Don't fight me. What are we doing? So you get exactly right things. Diameters are roughly the same thing as circulars. None of these will cross. Ooh. If you use plus or minus 2, you get dotted lines which cross all over the place. And then for some reason the author, Alan Hatcher, has counted how many times these cross and how many regions you get on the inside, which makes me think that maybe Hatcher knows a formula for this, or knows some result about how many times these will cross for plus or minus 2. Possibly mumble related to solving other sorts of equation. Anyway. Megalomorph does great. Great addition to any Twitch chat, I would say. Highly recommended. So it's the time of year where lots of people ask me to write recommendation letters for them. So I've got that on the brain a little bit. Highly recommended Twitch chat. Everyone here is certified for being in a Twitch chat. If you're looking for somebody to be in Twitch chat, then yes. Right. Okay, so let's read the proof because the proof's important. Here are some matrices. Look at these. These remind me a little bit of the multiplying up fractions that I was doing before. I wonder what's going on there. Oh, they just have the same determinant. It just follows through. What? Induction starts by looking at these. That's all fine. All other edges add in stages. Okay, so we're going to check this actually works for all of these things before we do the converse down here. So other direction. Let's do part 1, part 2. And so on and so on and so on. Yeah, okay. So consider this determinant. If we know that AD minus BC is plus or minus 1, then when you put this number in, yeah, by induction, because you were building it inductively, determinant condition then holds also, because if you calculate the determinant of this matrix, I don't know why I'm writing it out, it's right there. We kind of had this calculation before. The AB's cancel, and you get AD minus BC, which is the same thing. And you can calculate that one as well, and it's all fine. So the determinant condition continues to hold. Is it plus 1 in some whole regions and minus 1 in some whole regions of this circle? So it felt like that was said it was actually equal to AD minus BC. So over here, oh, does it matter what order I look at them in? Yeah, left, right, or right, left. Because this thing is going to have the opposite determinant to this thing. So I shouldn't look at regions, I should look at directions or something like that. Which fraction is smaller? Do I mean that? I'm not sure if I mean smaller or more negative. Are they the same thing? Okay, jury's out, but since direction matters anyway, I'm not going to look for which particular regions. Oh, maybe I could look at this diagram. Would that hurt? I'm not enjoying looking at this diagram. So a more negative number? Positive numbers first. So I look over here, then I get things like 4 minus 3. If I read left to right around this bit, I get things like 6 minus 5. These consecutive ones are all connected. 5 minus 4, so I get 1. Reading this way, I would get minus 1 if I read the other way around. Over here, I get 9 minus 8, 6 minus 5, 6 minus 5 again. Okay, So I keep getting determinant 1, and then if I keep going round this way, so this is going to be the question, do I keep going round? I think I do, because then I get, so first thing would be -1, 4, second thing would be -1, 3, and then the determinant of this is -3, take away -4, which is still 1. So then I think the rule is if you're reading, I should probably check what happens if I pick a point up here and a point over there. Oh, but they're not connected. So maybe they don't have determinant they're plus or -1 anyway. Okay, yeah, I think it's to do with the direction around the circle you're going, but globally around the whole circle, not 1 in some region, -1 in some other regions. I think that's fine. And because the circle is arranged in order, more negative numbers over here, more positive numbers over there, I think you can equivalently say, instead of clockwise or anti-clockwise, I think you can equivalently say that if you write the larger number more closer to positive infinity first, and then the smaller one next. I love that that's replying to, you can't quite get this in the Twitch chat, but the @ symbol is replying in particular to the point where Megalomorph said, "It's my motto as a professional troll." This reply of how do we classify these spaces? How do we classify these spaces? What's a modulo space? This is like reply. So you say you're a troll. Here's a maths question. Perfect, love it. I'm sure that's how Twitch chat normally works, right? If someone says hi. Don't feed the trolls, but do send them tricky maths questions. And I know Megalomorph's typing at the same time as that. Right, good. Okay, converse. If this is plus or -1, then there is an edge. That sounds hard to prove between these. So let's read it rather than trying to guess it. We're going to look at the positive bit. Fine. Okay. Interchanging the matrix multiplies by plus or -1. We had already thought of that, so that's nice. If you're looking at one of these infinite fraction-y sort of things, then that's a case that's sort of separate. It's not too bad. Feels like doing the induction thing again. Right. So then we can assume these things. Fine. Okay. So check the kind of special infinity points separately. So I meant about once if you add it in, you have to remember you added it in. Adding a new triangle to the diagram creates 2 new edges corresponding to the matrices formed by replacing one of these sum of 2 columns. Oh no, matrix theory. For each matrix of this, it's possible to perform a finite sequence of the inverse operations of subtracting one column from the other. Hang on a minute. Yes, carry on. A finite sequence of inverse operations subtracting one column from the other and end up with a matrix that we already know corresponds to an edge of the diagram. Subtracting the column with the smaller second entry. That feels a bit like a kind of algorithm approach, doesn't it? Column with the smaller second entry from the column with the larger second entry. So we keep having negative numbers, so keep having positive numbers. Stop when they become equal. The difference is strictly decreasing. When you do the difference, yes. So for this, the difference between these numbers is strictly decreasing because you subtracted. It's still positive. What if the second number wasn't more than twice as large? Well, it won't be. What if it was only just a little bit larger, like 8 and 9? That makes the difference larger, so I should be careful. Subtract. So this is a fun process. You've got a pair of numbers, and you subtract the larger from the smaller. And what I briefly thought was that the difference between the two numbers would go down, so it would finish in finite time for that reason. But that's not true, because if you replace the larger number with the difference, you might be in a situation like this, where the numbers are close together and then you get numbers that far apart. Of course, that's not a problem, because this will now just carry on going, but I need to be more careful if I'm talking about subtracting the difference between these things. Something that is true is that the largest number gets smaller when you do this process, so this will terminate in finite time because the largest number you can see has to get smaller. Even if this was only 1, we'd be subtracting 1 and be getting smaller. Okay, so then we end up with this, and the last matrix corresponds to that edge. and then reversing the steps shows you how to fit it into the diagram. Brill. So in a way, we're talking about matrices of this form with determinant plus or minus 1. We're talking about how they can be made. What are these operations really? So if you're adding the columns, that's like multiplying by 1101. If you're adding the first two and putting the sum, replacing the first column, it's like multiplying by this matrix. And if you're adding the two columns and putting that sum in replacing the second entry, that's like multiplying by this matrix. So then I think the result is that these two matrices generate the set of matrices with integer. I think the result is that these matrices with determinant plus or minus 1 are generated by products of these matrices, I think. Ooh. Yeah, which feels like a matrix fact that I should know. There's Megalomorph. Thanks for typing your response, Megalomorph. Sorry I made fun of you. I don't understand it at all because I haven't been following it, because it's not a sort of maths I know anything about. But view an elliptic curve as a quotient of C by lattice. Describe pairs of vectors, but different pairs can generate some vectors. Quotient out the equivalence. Okay, look like a quotient with a nice space for the group action space. Oh, that's nice. I know what some of those words mean. Okay. There was a comment that this works because GCD of A and C is 1, which I haven't quite followed. I haven't been thinking at all about what happens up here. Yeah, why does it have to happen that you end up with something like 1, 0 along the top? Oh, right, it's coming up down here. I was worried that I had to understand. I was worried that I had to understand that from this paragraph, but there's more argument still going. Okay. We subtract the column with the smaller second entry with the column with the larger second entry and repeat. We cannot get 0 in the second ring because they would have had equal before. Once we get matrix with equal entries in the second row, these entries will divide the determinant, which is plus or minus 1. Oh. Oh. Yeah, it does remind me of the Euclidean algorithm, right? Through repeated subtraction. I think it might be that. Yeah, it is that, isn't it? It's Euclidean algorithm, right? And the determinant stays the same on the way down because the determinant of these is plus or minus 1. The determinant stays the same or changes sign. So you end up with one of the. If your determinant started as plus or minus 1, for example, in this example, 57 taken by 56 is 1. So A and C differ by 1 at the end. And there's an edge joining one of the large semicircles in the upper half plane diagram. Oh, I thought they were going to tell me that n is 0. Oh, in the upper half plane diagram. That was the one with the straight line, x-axis. N plus 1. Right, so the first step, the n plus 1 is joined to n, is joined to 1 over 0. Because we saw that the whole numbers disappeared off in the original model. The whole numbers disappeared off towards 1 over 0, and each time you did another round of it, they were definitely joined up. I guess what I'm saying is that the nth power of that matrix over there, the nth power of that matrix is, I believe, this, which shows you that 1, 0 is joined to n1. Because when you draw the medians, you have a line joining that to that. Yeah, this median rule is all to do with those matrices, I think. Seen this matrix before, of course, because this matrix I think is also helpful for generating Fibonacci numbers. I think. If you apply this to... Oh, maybe I don't mean that. Yeah, not quite this matrix. It is important for Fibonacci numbers. Yeah, the Fibonacci numbers, I think, are generated by powers of this matrix. B, so it moves B up and it sums them and puts that up. No, I'm wrong. Now I want to do my Fibonacci factor, of course. Anyway. Yeah, okay, right, good. So those were joined, and then because these are joined, this number turns up in between. In the next round of calculating medians, you get this fraction because some of the tops, some of the bottoms, yeah, plus 1 over 1. Okay. So when we do this sequence, we might not get 1, 0 at the top, we might get 1, n at the top. But that's okay. We know how to build that. I think my fact is still true that if you can build it out of powers of this matrix and powers of this matrix, then that gives you directions through the fairy diagram to get to where you want to be, following lines along the fairy diagram, I think. Not fully certain though. Yeah, something like this. Does the matrix actually represent the connection? Yes, the matrix represents the connection itself, I think. But the circular arc that's drawn, I think, represents that matrix with determinant plus or minus 1, because sort of depending on direction that you read the line in. Thank you, maths. Right, so the fourth possibility of where to put 0, not the one I said, not the one I wrote. Fibonacci numbers generated by... So where are you going on? That's one of the ones on my board, isn't it? No, it's not. That's also not the one I wrote down. Good. Because if you apply it to... Sorry, the joke for the Fibonacci number thing is that if you apply this matrix, thank you maths in chat, to the pair of numbers A, B, then you get A plus B, A. So if A and B were two consecutive Fibonacci numbers, with A the larger one, like 13 and 8 in your Fibonacci numbers, those are two consecutive Fibonacci numbers, then when you multiply by this matrix, it's really cute. It calculates the next Fibonacci number, which is 13 plus 8 is 21, but it also holds 13, it keeps that hanging around because we'll need that for the next sum that we do. It kind of stores enough information to remember the most recent Fibonacci numbers. So then you just calculate powers of this matrix, and that gives you Fibonacci numbers. Off they go. It's not sorcery. It's just, I guess, you can turn recursion relations into matrix operations like this by just saying, if you've got a formula for generating the next one as a linear combination of the previous ones, then you just write out, that's what this first column is doing, right? It's telling us to do the sum of the previous things. If you had some general linear combination of previous terms, you could write out some matrix that said, you want to sum 3 times the previous 5 terms, well, I'll write out 5 3s for me. And then this bit over here is just saying it's to shift down the data that we already had. It gives me B. Maybe B was supposed to be larger. Whoops. I think B is supposed to be the large one? Yeah, I've multiplied my matrices incorrectly. Okay, flip all the A's and B's in the thing I just told you. I want to see 8 over 13. shifts the data up, down, sideways. Now I've got confused. I want the matrix that does this, and I'm not certain it's this one. Yeah, I can't multiply. It was A. I was right the first time. Ignore the last minute and a half of things that I've said. This was used as a step question a year and a half ago, which is slightly annoying. I've been doing versions of this fact for several years, and now it's in a step question. Lots of people have seen it. So taking something that I've been using as a cool maths thing and turning it into a past question exam thing. Okay. We're doing recursion relations. There's algebraic geometry happening in chat. We suspect that powers of matrices are useful for helping us understand the geometry or maybe topology of some shape. Not really clear on that bit. And this is so that we can understand number theory, and in particular Pythagoras' theorem, which is famous for being part of geometry. Just sort of everything, right? Oh yeah, you should diagonalize that matrix. Once we've worked out that matrix for the Fibonacci numbers, you should diagonalize it, and then you get Binet's formula for the Fibonacci numbers. That weird formula with the powers of golden ratio. It's kind of cool. But also, fun fact, you can then generalize to other recursion relations with constant coefficients and a fixed number of terms. Mumble. Anyway, which we've used, I'm sure, before, because I think there was a bit of this live stream experience where I just went on and on about the Fibonacci numbers, which is tri-Fibonacci numbers, with TRI at the front, where you add together three things. And they've got some sort of predictable properties if you write out some 3x3 matrices. They're kind of the same. What was I doing? I was doing this bit. Oh yeah, okay, so we think that there's some sort of Euclidean algorithm shaped thing going on. We think that we're generating these things with pretty simple matrices. I think the matrices represent somehow the arcs in the diagram, and that if I labelled each arc with a factorization, possibly up to a transpose. Is transpose flip determinant? That's a stupid thing to say, isn't it? No, come on. Possibly up to flipping the order of the columns. I think we could understand all of these arcs in terms of pretty simple matrices. Who knows? There are connections everywhere. That is a good lesson. Right. There you go. The sign tells us which is larger. We kind of worked that out earlier, but now we can see it in black and white on the page. I don't feel like I finished reading this bit. Reverse the sequence. Okay, it's just kind of conclusion. Good. Interesting consequence. The median always produces labels that are fractions in lowest terms. That is good. Why is that a consequence? If they weren't, then their determinant wouldn't be 1 because the column matrix, right, of the thing that you built. If it were always true, the median of two fractions in lowest terms is again in lowest terms. Oh, that's not always the case. Okay. Somehow cases like this do not occur in our diagram. No common factor. Prime factors A and B have no prime factor in common. A and B are co-prime. Hey, nice word. Alternative terminologies say they're relatively prime. Okay. Each labelled vertex AB is joined to some other labelled vertex C over D by an edge of the diagram. From the moment it's drawn, it's joined to two others, right? Oh, I guess to start off with, there's only the diameter. Okay, yes. By the easier half, we have the determinant is plus or minus 1 because of the way you constructed it, going top down from the start inwards. Any common divisor of A and B must divide the products AD and BC. Yeah. Yeah, because the determinant wouldn't be 1. If you made something along the way, do I have to worry about D and C? Also the difference. No, I don't really have to worry about D and C. there just would be some common factor. If there's some common factor between A and B, then, well, where did you make this from? What does it join to? Show me something it's joined to. Let's go. There's a determinant 1 over here, and hang on a minute, your matrix for making that determinant, right? A over B, C over D. If this has got a common factor in here, then your determinant is going to have a common factor of magnitude that much. I don't have to worry about what C and D is, just the fact that it's connected to something else in the diagram. That is weird. That is weird. That's a sign we've maybe done something that we didn't understand. Finding things weird. I guess. Maybe not. Maybe things can just be weird. Good. Okay. Every fraction appears in the fairy diagram. Assume is symmetric. P and Q are non-zero. So how are you going to find me the thing P over Q? Right, we need these numbers to give us plus or minus 1. Now that sounds like Bezout, right? If they're coprime. Yeah, why are we not doing Bezout yet? This feels like a Euclidean algorithm is going to be relevant here, right? You're in a country where there are two sorts of coins valued P pounds and Q pounds. You can give somebody some multiples of the P pound coin, and they'll give you some multiples of the Q coin in change. Can you come up with some series of exchanges like that where you've successfully paid for something that costs exactly £1? There's a formula for it. There's a Euclidean algorithm, right? You run the Euclidean algorithm, you reverse it to find S and R. Here we are then. Yeah, okay, so I can calculate these coefficients using Bezout, right? And then I've got two numbers about. Do I know that R over S is in here? I won't know whether or not. That's not enough, is it? So I need to prove that they're actually. Have we got that? Okay, let's read it. Okay, procedure for repeatedly subtracting. Yeah, okay, we're going to run this version of Euclid. Wait, what's Maths 222 saying? There's a bijection between rationals and integers. Yes. So is there a bijection between integers and Pythagorean triples? Yes. These things are both countable. I guess surprised that z squared is countable, but these things are countable, so there's a bijection. There's several ways to do it, but any of them would let you put the Pythagorean triples in order if you wanted to. I don't think the order would mean anything, but you could line them up. You can list them. They're countable. I think that's okay. Yeah, the bijection between the rationals and the integers is the fun bit, where you say, aha, Pythagorean triples. Although on the other hand, you know that Pythagorean triples are countable for a different reason, which is that Pythagorean triples are made of 3 integers, and z cubed is countable. So if you like, assign an integer to each point of ABC. Each triple ABC has an integer associated with it, and then read along the number line. And if that number corresponds to a Pythagorean triple in 3D space that you haven't met yet, whatever you want to do, count them in that order. I guess the fact that they're like z squared instead of z cubed is kind of fun, but unfortunately those things are the same size. So it's kind of weird. Anyway, infinity's weird. Yeah, next stop, Cantor. We've done the weirdest intro to countability ever. Step 1. So we'll talk about Pythagorean triples and matrices. Okay, what are we doing? We're doing another. There's a square down here, which gives me hope that we will read this and it'll all make sense. I vaguely thought about running Euclid's algorithm to find R and S. Well, you run Euclid's algorithm, reverse it for Bezout to actually calculate R and S. But then I realised that I wouldn't know if R over S was on the fairy diagram or not. I could vaguely hope that it was a smaller fraction, but I don't know what I mean. So I'm going to do this, which I strongly suspect is related to the Euclidean algorithm, but keeping track of things a bit more along the way. Here we go. Procedure for repeatedly subtracting what colour does not affect coprimeness of the 2 second entries. No, we're good. This is also how you talk about Euclid's algorithm. So the procedure is applied to this. The results of matrix whose second entries are equal and co-prime. Oh, somebody showed me this once. This is ringing a bell for me. Somebody showed me this as a better way of doing Euclid's algorithm that also calculates the Bezout things along the way by sort of keeping track of it, a sort of different sort of bookkeeping. They had it the other way up with P and Q upstairs, but I think this is going to turn out to be the same, so let's read it, because I can't exactly remember what it was. Sorry, Mario, if you're watching. I remember you told me, but I don't remember what you told me. Let's choose a matrix of determinant plus minus 1. Use two laboratories of 1, say this one. If we start with this matrix, apply the reverse of our sequence of operations. 1's in the second row. What? Oh, the reverse of this. Okay, so you're going to reverse it to get 1's, and then you're reversing it for Bezout. Yes, okay. Resulting sequence. I'm just saying Bezout and Euclid over the top of this perfectly good text because I've already seen Euclid and Bezout, and I'm trying to get everything to resemble those. There's a meme that you see sometimes of. The meme is something like a man who has only seen one movie compares every film to that movie, which sometimes feels like me reading maths books. It's like, aha, adding. It's giving me strong sense that this is all about adding. I do a lot of summer schools. Last year I did 7 summer schools, and that was a bit of an unusual year, but yeah, not that unusual. I've been around a while, so I don't want to think about how many summer schools I've been on. Most of them in a teaching capacity, but you still learn loads of stuff in a teaching capacity. Right, okay. We're going to convert this into the same determinant plus minus 1. This means we found it integers in RNS. Yes, okay. Oh, what? Was that good enough? Oh, so the thing I thought it was going to explain to me. Oh, if this thing is 1, I was not paying attention to proposition 1.2? If the points... I didn't believe this in my heart, right? We talked about it, but I didn't believe it in my heart. That each pair of fractions, if the determinant is plus or minus 1, then there is a line between them. They are connected. It's part of the fairy diagram. It's in there. So in particular, if you just start with A over B and you magically construct C over D, maybe using Euclid and Bezout, my favourites, then you can, if you construct it so that it's plus or minus 1, it's co-prime. So yeah, okay. If you construct it so that this is true, then you get to use the if part of this to say that there's an edge in the fairy diagram, which necessarily means that there's part of the fairy diagram you at some point calculated it as the median of something. That is good. And it's just Bezout, really. We're keeping track. We're doing some bookkeeping along the way to work out the Bezout coefficients, but also being slightly vague about saying, I feel like this process is Bezout. And a good exercise for a keen student would be to take the numbers, or take some examples of P and Q. Choose some examples of P and Q. Work out the sequence of operations by doing this subtraction with the differences. Work out the sequence of operations. You won't be able to fill in the top of the matrices yet, but work out the sequence of operations and write down notes of what you're doing on each step to turn P and Q into 1, 1, where the process stops. Explain why you get to 1, 1, and then write in 1, 0 at the top and reverse your steps to make it kind of true along the way. The notes you were making along the side about what subtraction you were doing should be true for the top row as well as the bottom row, and then you'll end up with the matrices where all of them have determinant minus 1 or something. Say this one. We picked this one. It's got determinant minus 1. No, it's got determinant 1. I'm an idiot. So reading up, all of your matrices will have determinant 1 because of these row operations that multiply by matrices of determinant 1 or minus 1. Maybe I mean plus or minus 1 for that. I think I mean plus or minus 1. All your matrices will have to determine plus or minus 1. So right at the top, you've now got numbers x and y, such that xq take away py is equal to plus or minus 1. Which sounds magic, because that'll be a solution to this. And then once you've got this, the determinant is plus or minus 1, so there's an edge of the fairy diagram. That feels like a good place to kind of wrap up. It really is Bezout. I've now decided that it's Euclid's algorithm and Bezout, the thing that we're doing here. With the repeated subtraction, or I guess you could do division. And then upstairs, there's some sort of bookkeeping that I haven't quite followed to do with the coefficients, or the quotients in Bezout. And maybe I should do my own exercise, right? To follow through what's going on. That feels like a good place to pause. If you only have a hammer, everything looks like a nail. If you only have Euclid's algorithm for positive integers, then everything's going to look like an attempt to solve ax plus by equals c. Okay, is this the end of section 1.1? We've hit some exercises. Is my exercise one of them? The exercise that I just kind of made up. Is it that? Mary's going to collect some points. What are you going to do? Are you going to collect points for hitting 4 o'clock? Okay. I don't know how points are. Ooh. Right, okay, reduce these. Use property in 1.1, double anything non-negative. Wait, to get to these matrices. Oh, this is the original line that goes right across the middle of the page. We actually talked about going up to the top as well, or down to the bottom. Determine that the following statement is always true. It doesn't look true, does it? If you take the medians of large numbers, you always get a larger answer than if you do the medians of smaller numbers. True, so on another line. Dip, 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 dip. If median was just the middle, then this would be false, because I could make these true. This would be true. Yeah, because the average is half of each added together. Come on, James. Is it called extended Euclidean algorithm? Is that the thing I should Google? Thank you, Neutrino. I think you have saved me for it looks like the same thing. Yeah, to calculate the quotients at the same time, right? Yes. Actually go. Good. Okay. I'll have to read that. Oh, sorry, Megalomorph. Wait, what? Oh, Neutrino said it as well. Oh, no, sorry. I haven't been keeping up with chat. Oh, dear. Right, well, point is Mario told me about this about a year ago. And then I forgot the name. Yeah. They're not fighting each other, they're just... What they're both fighting against is my terrible attention span and my ability to read things. For me, Megalomorph's comment is still on screen, so it's just my inability to read things that are literally in front of me, which we've seen from this bit as well, where the answer is often there and I'm looking there. Good, right, reading books is fun. Request for homology groups, I'm not sure I know what those are. I think you asked about homology groups earlier, and I thought, yikes. Proper algebraic topology, isn't it? Right, good. Not the sort of thing I know about. And I'm having fun with this. Oh, yeah, they have section 1.1. Next up, section 1.2. Very series. There they are, some numbers. Did you make it to you made it to the timer? Yeah. I think Maths 222 is studying. What are you reading? You told me before there's a book that you're reading that's about, is it a topology book? That's doing a lot of topology from like first principles, and then you've learnt lots of topology. I'm trying to keep up with who does what. Like I'm trying to remember Megalomorph's algebraist. Maths 222 is a topology person, I think. Yeah, Hatcher also has things to say about one of these. There you go. Cross-Lee's central topology. That was it. Yeah, I don't remember what maths people know, if any, like me. I know fluid dynamics. We don't do much fluid dynamics on this live stream. I'm a bit worried that I don't actually know any fluid dynamics anymore, and that was really the only thing that I knew back in the day. Okay, if I can back and forwards. Yeah, okay. I feel like we've got a fair amount of time to section 1.1. We have made it to, what was that page? 36 out of 106,792 or something like that. 35. And so long as Hatch doesn't write another 10 pages before next week, we might be able to catch up with section 1.2. Homology was Hatch's first book. Is it also available? So okay, Hatcher homology. Alan Hatcher page. What can we learn about? Books, topology of numbers, algebraic topology. Books. Download page. Yes, you could be reading about algebraic topology right now. It's an unfinished book. Earlier plan. Ooh, right, okay. Current version of this chapter. Okay, right, it's page for sequences and then topology of numbers. Somewhat geometric point of view. Okay. Electronic version will remain freely available here. That's nice, isn't it? Good. Oh, so the previous ones. Okay. Other projects are available. Other maths is available. There you go. So algebraic topology by Hatcher Corner explicitly. Freely available and cheap if you want a printed copy. I did not know that. So the story for me is just that I knew none of this, but I was on, for complicated reasons, I was on a summer school trying to explain Euclid's algorithm. And one of the postdocs that we had around told me that I had to read Hatcher's topology of numbers. And look at me, a year and a half later, I'm finally, I think they met before the end of the week, but a year and a half later, I'm finally getting around to reading section 1, which feels pretty Euclid algorithm. So partly I mentioned Euclid's algorithm because one hammer, everything looks like a nail, but partly because a postdoc told me explicitly in the context of me trying to explain Euclid's algorithm that I should probably go and read this book and talk about Euclid's algorithm, informed by what I found, I think. Good. Okay, right. I'm going to call it there, I think, because it's 4:05. Good to see you all again. Have a nice week. If you follow my other projects, Oxford Online Maths Club is starting up again on Thursday. This is a sort of super curricular maths live stream where I get whenever I can, I get Oxford students on the show to talk about maths that they're interested in. That's on my kind of work channel, Oxford Mathematics Plus. We've got one of my students on Thursday talking about fundamental theorems. Next week we're doing some puzzle solving. We've got rough plans for the rest of the month. So that's the other project that's running at the moment. Otherwise I'm back. It's on, so work project is Maths Club. So during the working week, I do a stream on YouTube with links that appear here. So that page has got links to like last year's episodes and the year before, because we've been going since the pandemic. Oxford Online Maths Club is especially aimed at high school students who are about to finish high school or about to apply to universities. We're trying to give people a sense of what university maths is like. So not this is too hard for Maths Club. But if you know people who are in England, I would say year 12 or year 13, people who are doing, I don't know, A-levels or International Baccalaureate or SATs or AP courses or something like that, people who think about university, Maths Club might be the sort of thing they want. look, I'm advertising Oxford stuff on Twitch because I advertise Twitch stuff on Oxford. One of those things feels wrong, and it is the thing I do more often, which is to advertise my personal Twitch on my work stream. But so in balance, I'm advertising my work stream on my Twitch. Doing promotion. Right. Other things we're supposed to advertise? No, that's probably enough advertising. There's a lot of stuff to do at that level. It's a good level. It's where most of my work feels like it's aimed at people of ages 16 to 18, which is a very narrow slice of the world, but lots of my work in Oxford is aimed at people aged 16 to 18, roughly speaking. Maths itself. You might also be interested in the concept of maths, where you can prove that things are true and know that thousands of years later they will still be true, and possibly be still things that people want to learn about. And you can't say that about many things. Right. Okay. Best of luck, everyone, with other endeavours, and maybe see you around on Thursday on YouTube or Sunday next week on Twitch. I think probably next week I'm going to have another go at bits of this. Otherwise, will get ahead of me. Right. I cannot remember how to stop the stream, so I'm just going to press random buttons until it stops. I'm stopping the stream. Have a good week. Bye. That one first, and then the mute button, and then the end. Right, okay, 2.